let me start with a very quick review as to where we were. So we started with a log Calabi-Yau, x comma d, and we built this dual, what I call a dual intercession complex, this pair BP. I defined the notion of a wall structure, a scattering diagram, which is this data structure telling us how we glue together some standard pieces. For every chamber here, or every space in between walls of the scattering diagram, we have a natural choice of this canonical model, these open sets are called UX. And the scattering diagram gives you some rules for gluing together those open sets. And then, assuming you have a certain degree of consistency, which is, by the way, vacuous in 2 dimensions, you get a well-defined gluing of a whole bunch of pieces. And in general, it's sort of hard to see what you get from that. So let me try to do one running example. Which is to go back to this example where we blow up P1 cross P1. So we start with P1 cross P1. We choose a point over here, and we blow up this point X, blow up X, and we get something that looks like this. And there's an exceptional curve E, which I don't take to be part of the boundary. So the boundary is the strict transform of the boundary line that was containing X plus D2 plus D3 plus D4. The boundary D is some of these 4 boundary divisors. E is not part of the boundary. Okay, so if you recall, one of the things that we need to do is to take a monoid I was calling P, which contains all effective curves. So we need choice of P, or not necessarily effective curves, but curve classes represented by stable maps. We need a choice of P in the second homology of this. So this is Z cubed. And I can take P to be represented or be generated by the following classes. So I take the class E, I take the class D2 minus E. So D2 minus E is this curve here. So that's the strict transform of the red dotted curve that passes through X, the straight line that passes through X. Ups, we pull it back and move E. And then I also take D3 minus E, which is, well, let me just take D1, same thing. Okay, so this is actually a basis for H2 of XZ. And so the monoid ring C bracket P is in fact isomorphic to C bracket T1, T2, and T3, the polynomial ring in 3 variables, where these 3 correspond to T to the E, T to the D2 minus E, and T to the D1. It's sometimes helpful to realize that these monoid rings are just things like polynomial rings or generalizations of polynomial rings, so that all the notation doesn't overwhelm you. And I'll also define if this ring, grand ring I'll call A, let me also define AN to be C bracket T1, T2, T3 modulo the nth power of the maximal ideal. So this was the kind of ring I was talking about last time where I said, well, let's take C bracket P modulo an ideal such that's a finite dimensional vector space. So it's enough to do the construction of these ANs for all N. Okay, so that's the starting data. And then I need to give you a scattering diagram or a wall structure. So if you recall, BP looks like, let me continue my color coding where the the rays of one-dimensional cones of P are in red. And then my scattering diagram, D, is going to consist of two walls. The first one sits on top of this ray in P and has an attached function, FD1 is equal to 1 plus T to the E. So let me write this T1 to fit with the notation up here, T1, times Z to the minus 1, 0. So here I'm using this, the embedding in the plane, as you see. Minus 1, 0 is the tangent vector to this ray, or to D1 pointing to the left. So that's D1. And D2 I'll take to be sitting on this other ray. It's D2. And FD2 has a similar shape. It's given by, T2. 1 plus T2 Z to the 1, 0. And so this time, of course, 1, 0 is viewed as a tangent vector here. Okay, so these things all make sense. Okay, so it turns out this is the scattering diagram you need. Because this example is in toric, there is, in the affine structure, there is a singularity here. And that's something we should keep in mind, that I haven't really, this affine manifold doesn't just embed an R2. There are different charts. So you have to be careful when you're thinking about charts for this. Okay. So now, there aren't that too many models we have to worry about. So we have a copy of C star squared for each of these four chambers. Each of these chambers gives us C star squared, and then each array is going to give us some local model that essentially covers these regions. So if we take n equal to 1, so let me say this now gives the construction, the gluing construction. There, gluing construction yields, I was supposed to read yields, varieties or schemes, I should say schemes, which I'll write as X circs of n d for n greater to 1. So notice, let's understand what happens when n is equal to 1. When n is equal to 1, we're just dividing out by the ideal generated by T1, T2, and T3. So we just get C. All of these TIs are 0. As far as we're concerned, these functions are just 1 and aren't going to play any significant role. So then it's easy to see n equals 1. In fact, X circ, well, 1D is a union of 4 affine planes, 4 A2s. With the origin removed. So if I were to draw this, I'd essentially be drawing the same picture as what we have over here. So what it looks like is we have a bunch of A2s. We remove the origin. We have an A2 here. We have an A2 here. We have an A2 here. And we have an A2 here, but none of these contain the origin. There's a point missing. And these open sets I've been talking about, so if you look at the open set, the interior of this affine plane, in the sense of remove all these other A2s, you just get a C star squared. So you have a C star squared here, C star squared here, C star squared here, C star squared here. Right, so each of these, this interior corresponds or gives it is a C star squared. And a neighborhood here, say if you take a look at this neighborhood, this looks something like spec C bracket Z plus Z minus, and then Z to the 0 plus or minus 1 modulo Z plus times Z minus. That's the local model. Once we set n equals 1, the ideal, all the TIs are in the ideal. So this looks something like a union of two lines cross A1. And that's what we're seeing here. This is the union of two lines cross A1. So we glue these together, and the only thing we miss is the origin. So that point isn't there. Now, for n greater than 1, what we're getting is some kind of partial smoothing. So if n is greater than 1, and 0 nd the partial smoothing. Now, I don't like the fact that this point is missing. This sort of corresponds to the fact that there was a singularity in the affine structure over there. The algebraic geometry is just reflecting the existence of the singularity. So how can I add in the origin? So here's a basic idea. So note that the ring of regular functions on A2 minus the origin is the ring of polynomial functions on A2. So this can be viewed perhaps as a version of Hartog's lemma, or Hartog's theorem. Hartog's theorem is a theorem in complex analysis, which tells you that if you have a homomorphic function on Cn, or on some domain in Cn, which is defined off of some codimension 2 closed subset, then it can be extended across that codimension 2 set. So homomorphic functions extend across codimension 2 subsets, complex codimension 2 subsets. So in fact, any regular function on affine plane minus a point will extend across the point to give you a regular function on the affine plane, and so it will be just a polynomial. Okay, so this suggests, one way to write this is A2 is just the spec of the space of global functions on A2 minus 0 of the structure sheaf A2 minus 0. So this is, that's just a way of adding a point in. The point is high codimension, so regular functions don't really see the fact that it's missing. So we can do something similar to this variety here. So let's call this, in fact, spec of gamma of on this x0 1d, so it's this order 1 order 0 thing, OX0 1d. So if I take the ring of regular functions on this gadget, this union of 4 A2s minus the origin, all of those regular functions is easy to see from what I just said. The regular function on one of these A2s extends across the origin. And if you have a regular function on the whole thing, well, that's a regular function on each piece that glue to on these axes. So of course, each of them extends across the origin because they agreed on these strata. They'll agree at the origin too. In fact, this is just a union of 4 A2s. So in other words, this puts the point back, this puts the origin back in. Okay, so let's call this now, this will be X1D. X1D now looks like a union of 4 F1 things. Okay, so that's how we're going to try to fill in the missing points in this construction. And in higher dimension, this is a two-dimensional example where we're just missing a point, but for 3 dimensions, we're going to be missing curves from the construction. We're always missing something codimension 2. So idea, you would like D, the scattering diagram, to have the property that gamma of X open I or D, OX open ID is, I'll put this in quotes because it's not immediately clear what this means, is big enough so that spec of this ring gamma X open ID, OX open ID, the spectrum of the ring of regular functions on the scheme we constructed is in fact gives a partial compactification of X open ID. Okay, so what this means is somehow you have to have enough functions on this to be able to recover not just the geometry of this, but the geometry of its partial compactification. So the key point is we need to be able to construct functions. Thus, we need to be able to construct functions on X open ID. So that's where the next concept comes along. So this is the key additional idea that we're going to need, past what I've already told you. And this is a concept which we call broken lines. Okay, so we fix the data. XD, P, scattering diagram D as above. Then a broken line for D is a proper continuous map beta from minus infinity, so I put minus infinity there, minus infinity to 0 to B with image disjoint from the singular locus of D. And we have a bit of additional information along with the sequence. Minus infinity is equal to T0 is less than T1, etc. It's less than TR equals 0, so a sequence of times in the domain of this now. So you need to have beta of Ti being the support of D for 1 less than or equal to I less than or equal to R minus 1. And for each I equal between 1 and R, the data of an expression AI T to the PI Z to the MI, with AI just some complex number, PI being an element of our monoid P, and MI an integral tangent vector. The B such that, so notice, by the way, you can think of this as living. Let me just write this. This could be thought of as being living in one of these rings, C bracket P bracket lambda sigma for some maximal count sigma. So maybe I should say, okay, I'll say that in a second. Maybe I say sigma I. Okay, so there's going to be a number of properties. This might look a bit overwhelming at first, but I think the idea is going to be fairly simple. So first of all, beta restricted to an interval ti minus 1 ti is a non-constant affine linear map with image contained in sigma I. So that's this sigma I I've chosen over here. So in other words, mi is a tangent vector to sigma I. And furthermore, the derivative of that beta, it's going to be affine linear, so as a derivative, that derivative is constant, and is minus mi for t in the interval from ti minus 1 to ti. Okay, so on each of these intervals, it's just going in a straight line, and the velocity is determined up to this minus sign, is determined by this exponent appearing attached to the interval. You should think of this exponent as being attached to this particular interval. Now the question is, how do we determine? We also want to have a rule for determining these. So the first statement is that A1 t to the P1 so that the M1 is just equal to z to the M1. So in other words, P1 is 0, A1 is 1. So the initial term is just z to the M1. Now, if you think about what this means, again, let me draw off the side here, draw a picture of our BP, and I will draw the broken line in black. So ultimately, the image is going to be some kind of piecewise linear path, still to be explained. So this will be beta of 0, and t goes to minus infinity out in this direction. So in other words, we're coming in from infinity. By the way, I use this word proper continuous map here. Proper just means that the inverse image of a compact set is compact. So it means that this has to go off to in some unbounded direction as t goes to minus infinity. Okay, so what this is saying, so if this point here is beta of T1, then this tangent direction here, we're running along in the direction minus M1. And that means in particular, M1 has to actually be a tangent vector lying in the cone. So in particular, I can think of M1 as actually a tangent element of the cone. So, okay, so that's how we start. So we choose some initial point inside the integral tangent vector to one of these cones. That's actually in the cone, so it's a point in the cone, if you will. And then we come in from infinity in that direction. It's parallel to that direction. I will do some more explicit examples in a minute. Okay, the next thing I have to tell you is what happens as we go from one domain of linearity to another. Okay, so for each I, AI plus 1, so the PI plus 1, sorry, T, PI plus 1, Z to the PI plus 1 is determined from AI T to the PI, Z to the PI. So these should be M's and MI plus 1 as follows. So there are two cases, depending on whether we're on a codimension 1 cell of P or not. So two cases. The first case is that beta of Ti lies in, let me call it point X, lies in the interior of the maximal cell. So the picture is that beta of Ti, as I said, that has to be in the support. We might have a ray. This is a, or almost a ray, a wall DFD. And we come in this direction from minus infinity, and we hit this ray. Now, what happens here is we then have, we have a wall crossing that. So the wall crossing applied to the monomial gives an expression. Well, I take these monomial AI T to the PI, set the MI, and then I multiply by some power of FD. That's going to be ND evaluated on MI, where ND, if you recall, was the primitive normal vector pointing in the half space in which the ray, this is coming from. So this is a primitive normal vector. Okay, so that was the wall crossing transformation applied to this monomial. One thing to note here, important point to note, is that this is always positive. This exponent is always positive. And the reason is precisely this rule about the direction broken lines travel. Right? The tangent vector to beta is minus mi. So mi is pointing in this direction. And so in particular, nd is positive on mi, because nd is positive on this half space of the tangent plane, tangent space. So this particular algorithm always results in positive powers of FD, which is actually crucial reasons that we were led to this formulation. Okay, so now this is maybe a complicated, very complicated expression because maybe FD is very complicated. Maybe we're raising to big power. So you could expand this out. So expand this out into a sum of monomials. And take AI plus 1, keep the PI plus 1, Z to the MI plus 1 to be one of these monomials. Okay, that is a choice, but there has to be one of these monomials will appear as the next ray. So you might have many, many different broken lines based on these choices, and that's also important. So that's the case when we cross a wall inside the interior of a maximal cell. The other case, case B, is when we cross a wall contained in a codimension 1 cell of P. So beta of Ti lies in the interior of rho, where rho is codimension rho in P. Is codimension 1. Okay, so if you recall there, I had a ring. We had this ring which looks like a bracket lambda rho bracket z plus z minus, and we divide out by the ideal z plus z minus, or the equation z plus z minus minus t to the class curve class d rho times f well, I think I was calling f beta of ti, so f sub x, where x is point where we cross. So we have this ring. So that was our standard model. And if you recall, we also had two localization maps. So we had, so let me try to draw a local picture of this here. So we have our broken line comes through here. We have a wall here that we're also crossing. And then we might bend here. So that. Let's call this sigma, and this is sigma prime. We had a localization map to A bracket lambda sigma and a localization map to A bracket lambda sigma prime. And what you do is you have the monomial AI t to the pi z to the mi. You lift it up. You can show that with this sign hypothesis, this lifts to, or there exists a unique element, I should say. There exists a unique, what's called alpha in here, which maps down to this monomial. And then this will map down to some alpha prime in here. Okay, so a priori, this map is, well, yeah, but let me just leave this an exercise. Convince yourself that this localization map, as I wrote down last time, actually has this in its image. And the main point is that we're really rewriting it in terms of z plus and elements of lambda rho. And then we're solving for z minus, we're replacing z plus with z minus inverse times this. So alpha prime might involve many different terms. And again, I take we take AI t to the, so AI plus 1, t to the pi plus 1, z to the mi plus 1 to be a term in alpha prime. So I'm really kind of doing the same thing I did over in case A, where I'm just multiplying by some power of fd. Effectively, this equation is implementing a multiplication by maybe I should have used fx before too. This is a product of such fd's, but we also have to take into account this quantity here. Okay, so that is the definition of Bergman line. I'm going to do an example in a minute, but I want to finish one key definition. Okay, so definition, and this is really the key point we're getting at. So let X be a point in B0. B0, remember, is the locus where the affine structure is defined. And we move also the support of D. So I want a point that doesn't live in any wall. And let's let M be a point. I'm going to write this as B of Z. This is an integral point of B. In other words, this is a point of B intersect div D of X dual. So if you recall, I constructed B as a topological subspace of the vector space given by tensoring this lattice by R. So now I'm going to intersect with the integral lattice, the dual. This was Hom div D of X into Z, which is just direct sum of the lattice generated by the DI stars. So we're looking at points of B which are integer linear combinations of the DIs. Okay, so in particular, if you have an integral point in a cone like this, it also corresponds to a tangent vector. So note if M is in sigma, P is an integral point, then M also defines a tangent vector to P. Okay, so now I'm going to define theta n comma x is going to be a sum of all beta, some quantity called monomial beta. This lives in, so here I want to fix some ideals, so I'll use AI bracket lambda sigma. Maybe I should use a different sigma prime. Let's say X lies in the interior with some sigma prime. Then I want to work in sigma prime here. So I can write theta mx as a sum of terms where beta is this runs over all broken lines with initial monomial z to the m and beta of 0 equal to x. So x is the endpoint of the broken line, and m tells us what direction from infinity we come in. Now, what's mono of beta? Mono of beta is the last monomial attached to the broken line, i.e. AR T to the PR, Z to the MR. Okay, so we take a look at all the broken lines coming in the direction M. There can be many of them because you have all these choices to make. And you look at those which end at the point X, and then you take the sum of all the final monomials. Okay. So, key definition. Say D is consistent if the theta mx patched together to give a regular function on X circ di. Okay, so the point is, I have this theta mx is defined depending on a base point. If I take a different base point, I can get different functions, but I can view those as living on different open sets of this covering of xid. And provided they actually patch together, I get a well-defined global function on this x di, and hence it's kind of global function that we want. Okay, so that's a lot of very technical stuff. The definitions I don't think are particularly hard, but take a bit of getting used to. Let me try to go back now to my example of that I started at the beginning of the lecture to show you some of the behavior. So if you recall, we have this scattering diagram coming from. I'm going to draw the picture a little bit differently now. So it's supposed to be a straight line. So we had these two rays. I had this 1 plus T1 z to the minus 1, 0. And this way I had 1 plus T2 z to the 1, 0. Now I'm going to put a little squiggle here. And this is a cut. So in other words, what I've drawn, if you cut out this left-hand horizontal axis from this picture, this is a well-defined affine coordinate chart. This really is an embedding in R2. However, as I said, I can't embed the whole thing as an affine manifold in R2. The other thing I can do is I can choose a different cut elsewhere. But for the moment, I want to focus really on the affine geometry that's happening over here, so I need to choose the right chart. So we have integral points. So let me draw the integral points on this. Well, I'm not going to draw all integral points, but some integral points. And let's take this one here, n. Let's take n to be d2 star. That's this point here, this vertical ray, the way I drew things. Maybe I should label these things as d1 star, d2 star, d3 star lives there, but doesn't cut. D4 star lives there. Those are the basis vectors for the lattice. Okay. Now let me take my point X to be over here. Actually, before taking it to be there, let me take point X over here. And let's look at broken lines for this point ending at X. So, what this means is that we have to come in from infinity in this sort of in direction minus n. So we have to come in from infinity like this. We initially have the monomials at the d1 star, or sorry, d2 star, and it then ends at X. Notice, because this isn't crossing any wall in the scattering diagram, there's no opportunity for this to bend. We just get a single broken line, and we get the equation theta m x in this case is just z to the d2 star. And you have d2 star as a tangent vector to sigma. So this would be sigma and sigma prime. I would keep down here. Okay, so that's the simplest example of a broken line. Okay, now let me move x. Let's look at a different point, x prime, over here. Now, again, I'm not going to draw this in yet, but again, we have something coming from infinity. But because over here we're crossing a wall, if we want to get to x prime, we'll have to cross this blue wall, and that gives us some opportunity for bending. And for that, we need to do slightly more careful analysis. So let's look at the ring there. We have the ring. Well, remember we have monomial ring, 3 variables. Maybe we divide out by some power of this. It doesn't really matter what we do there. Let's divide out by power. And then we have z plus, z minus, and then I want to think of this as z to the plus or minus 1, 0. That's the tangent vectors to the horizontal axis. And then we divide this whole ring out by the equation z plus, z minus, so the class of the curve d1 corresponding to this ray is just, well, it's t to the d1, which was t3, I believe. We look back, so let me double check that. Yeah, so t3 corresponds to t to the d1. So t3 times this function here, that's 1 plus t1, z to the minus 1, 0. Okay, so that's our ring. Now, remember also in defining this ring, I had to choose a tangent vector, which I call c. So I'll take c to actually be equal to d2 star, or just the vertical tangent vector. And then the point is that we had this monomial z to the d2 star. That's just z to the c. And again, I'm sort of expecting to remember quite a bit here. But under the localization map, so we have the localization map to our ring AI bracket lambda sigma. Under that localization map, z plus just got mapped to got mapped to z to the c, given choice of tangent vector. So in other words, this initial monomial, as we are heading down this way, lifts to z plus. And now we have the other localization map down to AI bracket lambda sigma prime. And that localization map was defined essentially by solving for z minus. So the point was that z minus, or z plus, is equal to z minus inverse times t3 times 1 plus t1 z to the minus 1, 0. And that maps to z minus here maps to z to the minus c. So that's going to be z to the c times t3 times 1 plus t1 z to the minus 1, 0. So thinking of c, thinking of our affine coordinate chart, this is also can just be identified with 1, 0. Sorry, 0, 1 vertical tangent vector. So let me write this now as t3 times z to the 1, 0. Sorry, z to 0, 1. plus T1 z to the minus 1, 1. Or putting everything as monomials, T3 times z to the 0, 1, plus T1, T3 z to the minus 1, 1. Okay, so this is what happens when we try to cross this wall. This z plus or zc gets turned into this expression. And now I need to take one of these two as the next monomial. So I have two choices. For the next monomial. So choice one is T3 z to the 0, 1. So I would like to draw this up here. However, I think I don't want to have too complicated a picture here. Let me see if I can do something fancy here. There we are. So if I am using this first choice, I came down from infinity. Let me erase some of this. I came down in the vertical direction from infinity. I cross here, something happens, and the new monomial is T3 z to the 0, 1. The only thing that's changed is the coefficient. If we continue to go due south, this is still in the direction 0, minus 1. So that's the first choice. The second choice is this other term, which you see over here, is T1, T3, z to the minus 1, 1. And that means I can now draw the broken line corresponding to that. When we cross the wall, we suddenly change direction, heading in the direction of minus of this exponent. That's 1 minus 1. So we head southeast. So those are the two broken lines that end up x prime. And we see that theta n x prime is just the sum of these two monomials, is T3 z to the 0, 1 plus T1, T3 z to the minus 1. Okay, so that is that's an example. And notice here that at least if you look sort of at the theta function we got up here and the theta function we got down here, they patch in the sense that they lift the same element of this ring, namely z plus. Notice this is essentially by construction, right? So z plus, so this was the theta function on the upper side of the wall, z to the c or z to the d2 star. That was the theta function. This was theta mx. It lifts to z plus in here, and the image of z plus is this thing. So these two theta functions, theta mx and what turns out to be theta mx prime, actually patch in the sense that they come from a single function on this, in this ring, namely the function z plus. Now you might say that this was sort of, this is blindingly obvious because I constructed these broken lines from the terms that appear in the image of z plus. But if you play around with this, you'll find that sort of once things get more complicated, it's not at all obvious that this works. Okay, so both of these, so theta mx, theta and x prime patch in the sense they are images of z plus. Now you can go through this construction for any point here, and what any point in B. And you'll find that there's some subtleties, and I think it's worth saying a little bit about this, and then I will. We're almost at the break time. So again, let me try to save some time by copying this. So one interesting thing is what happens as this point moves over to here. So if you move the point over to here, well, you'll find, of course, you saw the straight line coming down. But if this point is too far along, okay, and maybe I should say we saw this straight line here. That's all well and good. Let me move the point a little bit further. So in other words, I didn't quite draw what I want to draw. Let me move the point over to here. So you saw the straight vertical line here, but you no longer have room for a broken line of this sort. Because such a broken line would sort of have to look like that. And that's coming on the other side. So in fact, there is a broken line that looks like that, except you have to be very careful about which affine coordinate chart you're working in. As I said, we'd actually deleted this ray when I was embedding this in R2 as an affine manifold. So we actually have to be a little bit careful about what this broken line is, because we have to be careful about the affine structure. And in fact, if we had instead cut along here, I would have gotten an affine manifold that looks like this, or a chart that looks like this. Where now, instead of this pointing this way, it actually goes straight down. And in this picture, these two broken lines that contribute, there would be a broken line. This one now looks bent because we have cut, even though it is straight in the affine structure. We now have made a coordinate cut there, so it's the affine structure, the embedding doesn't extend across this cut, and then the other broken line becomes straight. So in other words, there's a subtlety to these broken lines. Both of these broken lines in this picture, here or here, are actually straight lines. They don't do any bending. And if you go a little bit further along, the x triple prime, then you will get the vertical broken line and one that goes like that. So actually, there's quite a lot of subtlety about how these things behave, and it's not obvious these things patch. But if you want to do as a rather lengthy exercise, check that these things patch. Okay, so let me just end this first hour. Is the upshot. We can prove, so this is in a sense the theorem, that if D is consistent in the sense that theta functions patch, theta mx is patch, then in fact there's a nice simple form for the ring of functions on this glued gadget. It's actually equal to the direct sum over all n in B of z. AI, that was a round ring, the monad ring C bracket P mod, just quick reminder, C bracket P mod I, times one of these theta functions, theta m, where theta m is the global function obtained by patching the theta m axis. Okay. So this gives, if we have consistency, we have a lot of functions, and this is in fact sufficient. This implies that spec m of x id ox open id is a good partial compactification of x open id. Okay, so I think this is a good point to take a break. What I'm going to do in starting 10 minutes time is to explain now how to view this ring a bit more abstractly. Right? This is a ring you could write down without knowing anything about D. Sorry, this is I should say it's a module over AI that you could write down without knowing about D. So then you could ask, what can we say about the product on here? Can we sort of abstract away from that? But fundamentally, you should think of this as saying D records instant-on correction data. In some way, it tells us how to glue together the mirror variety. And you can think of this spectrum as a finite order version of the mirror. Okay, so maybe I should pause and ask for. Okay, so as I said, we now have this. So if we have a consistent, consistent scattering diagram, we get this description of the ring, and then we want to build XID as spec of this ring. So what I want to do is now abstract away a lot of this construction and ask, well, what does the product rule on this look like? And it turns out it's actually something that's somewhat easier to get a handle on. So what is the product rule? Very technical difficulties here. On this ring, let me call Ri, this is gamma of OX open ID, which has this description M and B of Z, AI times theta M. So I have a set of generators, these theta M's, and so let's think about theta M1 times theta M2. Well, that will be some summation, sum over M and B of Z, of theta M times some structure coefficient alpha PQR, where alpha PQR, sorry, I'll switch to notation M1, M2, M, where alpha M1, M2, M lies in our ground ring AI. Remember that C bracket E mod I. Okay, so that is, okay, I haven't done anything there. There's going to be some product rule that looks something like that. So the question is, can we describe this alpha M1, M2, M? So here is a simple theorem, and simple enough that I'll give you the proof. Alpha M1, M2, well, let me let Z be a point in B0 minus support of D sufficiently close to n, where n is this point here. Then alpha m1 m2 n is equal to sum over pairs of broken lines mono of beta 1, coefficient, right, it's a beta 1 times a beta 2, where the sum is over pairs of broken lines beta I for beta 1, beta 2 for m1, m2 respectively. Such that if I write mono beta 1, so the endpoint to be a beta 1 times z to the s1, where a beta 1 and mono beta 2, I'll say what that is in a second, mono beta 2 is an is equal to a beta 2 z to the s2 with a beta I, an element of ai, and s1 plus s2 should be equal to r. So maybe we require, so the first part is notation. I'm writing the last monomials attached to the broken line this way. I'm separating the part in ai from the monomial involving the tangent vector to b, and then I require r is equal to s1 plus s2. So we sum over all broken lines. I didn't say ending at z. Z was this chosen point near R. And we take the coefficients of the final monomials whenever beta 1 and beta 2 are broken lines for m1 and m2 ending at z, and with the exponents s1 and s2 adding to R. Okay, so let me give you proof. It's probably the only proof I'll do in this course. Expand theta m1 z times theta m2 z. And look at terms of the form a z to the r. So here z is this point. Let me try to draw a picture of what's going on here. R was a point here. Sorry, I meant n, not r. Sorry. This has to do with a slight change of notation in my notes from the usual. My usual conventions. We have m and we have z is sufficiently close. For the sake of this discussion, I must take z equal to m, but troubles n might not be a good one, might be in the support of d. We'll take z equals m as close to m as we want. Okay, so now we look at terms of form a z to the n. Now, if you how can such a term arise? So if you look at this expression here, I could just as well expand this right-hand side in terms of broken lines too, or in terms of the theta n at the point z. And the point is, how does a term AZ to the M arise from a broken line coming in from some direction? So it's not necessarily the fixed M that I chose over here, but some arbitrary M. So if we are coming in, if we have a broken line coming in the direction M, we notice we have the scattering diagram, the wall structure, that these will consist of cones. If we're coming in the direction M, or minus M, we're coming in straight to the point M, or very close to the point M. There's no way that this, if I trace back, is ever going to cross a wall. In order to cross a wall, I'd have to go this way or that way. If I go straight out, there's no room for a wall. So such a term, so we similarly expand, use different letters, summation M prime in B of Z, alpha M1, M2, and theta M prime Z. And note the only broken line which can contribute that can contribute to a monomial A times Z to the M is the broken line which doesn't bend and comes in from infinity in the direction minus M. Okay, and that broken line is a broken line for theta M Z. Not to theta M prime Z, but only to theta M Z because it's coming in the direction M or minus M. Okay, so that means that if you compare the two sides, on the left-hand side, these things, so if we expand this in terms of broken lines, you just get things of the form, well, you have a broken line beta 1 for M1 and broken line beta 2 for M2. And in order to get a term AZ to the M, the last monomials have to behave like this. Right? When we multiply this by this, you're going to get a Z to be S1 plus S2, so you need S1 plus S2 to be M in order to get a term in this expansion form AZ to the M. So the left-hand side, in the coefficient of Z to the M is precisely what we wrote down over here. On the other hand, that has to be the coefficient of theta R, or theta M, because no other broken line is going to contribute to theta M. And still, or is going to contribute to any theta M prime and give the exponent Z to the M. So the left-hand side, or the AZ to the M terms in theta M1Z, theta M2Z are precisely the terms appearing in the summation beta 1, beta 2, A beta 1 times A beta 2. And these terms are precisely the coefficients of theta M in summation alpha M1, M2, and theta M. Okay, so that's the proof. Okay. Any questions there? Yeah, so let's do this for our example. And now we're going to actually see that we get a much simpler expression. Rather than thinking about gluing together a whole bunch of things by some complicated rules, we're going to get some simple equations. So let's go back to this picture and get them to draw this chart here. Again, we had these two rays and scattering diagram, and let me compute. So we have 2 points here. This is D3, D4 star. D2 star, and I want to compute theta D2 star times theta D4 star. Now, I claim that there are actually two, actually, the other one I want to do, let me do the other one first because it's easier, D1 star and D3 star. Let's take theta D1 star times theta D3 star. I claim this is just T to the curve class D2. And where does that come from? So maybe I should say times theta 0, but theta 0 will actually be the identity element, so I don't really need it there. Let me choose a point Z near the origin, if I'm using theta 0. And now I have a broken line in the direction D1 star, comes in like this. There's no chance to bend. I have a broken line coming in this way, in the direction D3 star. When we cross the this vertical ray, all that happens. So here we had Z to the 1, 0, it's the attached monomial. Here we have Z to the minus 1, 0. But when we cross the wall, we actually pick up a copy of T to the D2 as a coefficient Z to the minus 1, 0. And that's simply from the slightly more complicated equation we have for the local models near these codimension 1 walls. So we have two monomials whose product gives Z to the 0, right? Z to the 0 times this, and hence we get T to the D2 times theta 0. And theta 0 is going to be the unit, so I should write that as T to the D2 is theta 0 is the unit. Okay, so that is the easy one. Now, again, for the sake of not having incomprehensible drawn, let me take another copy of this. This these. Now I claim here we have a slightly more complicated expression. Let me move this. So we're going to get two terms. So I'm going to take let's see, so T to the, sorry, color coding. I'm going to get T to the D1 times theta D1 star plus T to the D1 plus E theta 0, which again is the unit. So for the theta D1 star, I take the point Z maybe near D1 star. I have a broken line for D2, which is just the vertical line coming in. There's no chance for it to bend. And I also have a broken line like this, which just comes in. Again, this comes in the direction D4. It goes straight. I don't choose the one that bends. The one that bends would actually then give you canceling monomials. This tangent direction, that's, well, the monomial here is something, some multiple z to the well, this is z to the minus 1, 1. Right. 1 minus 1. Sine. This monomial over here, again, it picks up a copy of t to the d1 times z to the 1 minus 1. Before, this one will have attached monomial z to the 0, 1. And of course, when you multiply these together, you get this coefficient times z to the 1, 0, namely something pointing this way, or agreeing with d1 star. So that's this term. The other term comes from taking z to be near the origin. And this time I have a broken line that looks like this time actually bending, and a broken line that looks like that. And the monomials here is z to the 0, 1 again, and here will be t to the d1. If you think about the formula, will be t to the d1 z to the 0 minus 1. Okay, and that gives this term here. Okay, so we have a fairly now combinatorial way of describing the product. And it doesn't require knowing any of the algebraic geometry. It requires just having this affine manifold with singularities and the rule for defining broken lines, which is relatively simple. And then you can compute the product. This, of course, all presupposes that you actually have the correct scattering diagram. Okay, so rule is that we have a combinatorial description of the product once we have a scattering diagram. Now, why am I spending time on this? The reason is that I'm now going to take one further step back. Part of my goal in these lectures was to somehow trace the development. We had the SYZ conjecture. We had this idea that we should have some kind of corrections to the complex structure. We translate this into algebraic geometry in this way. And at the end, we get sort of a simple description for the ring and a product rule. And the product rule still depends on the scattering diagram. However, some 7 or 8 years ago, we asked ourselves, can we actually write down this product without reference to the scattering diagram? Because these scattering diagrams are somewhat complicated. And this led us to the following formulation. And this is what we call intrinsic mirror symmetry. Let's define the product structure on the AI module. That is Ri is direct sum m and b of z times AI times theta m. This was the ring we got from theta functions. Define a product on this abstract AI module without any reference to these things actually being functions on some variety. Define this directly by some Gromov-Witten theory of the pair XD. Okay, so now I'm going to say, let's throw out a lot of what I already told you about scattering diagrams and broken lines and so on. I just want to look at these pictures and try to reinterpret these kinds of diagrams as having something to do with Gross-Siebert. Now, there's a certain length of experience with these things, so it's still going to be a fairly big leap. But over the last 20 years or so, we have come to understand that pictures like this, or pictures we call tropical geometry, reflect certain kinds of algebraic curves. So I'm going to make the leap and reinterpret these kinds of pictures in terms of curves. So motivated by the description of the product group. We defined product directly on Ri as follows. So I'm going to give a very loose definition now, and I hope that in the last lecture I can make this definition somewhat more precise. So here, again, I want to define theta m1 times theta m2 as being some summation for m and b of z of alpha m1, m2, m theta m, and here m alpha m1, m2, m lies in C bracket p mod I. Okay, I haven't done anything different. Let me expand this out. This is some polynomial in monomials with exponents lying in p. I can write alpha m1, m2, m as being, I will use the notation n summation a and p of some number n a m1, m2, m times t to the n. Yeah, sorry, t to the a. A is a curve class. So now my goal is just to define these coefficients, and if I define these coefficients in some clever way, I'll have a product group. Oh, that's right. So we define NA M1 M2 M as a Gross-Siebert grant. Now this is going to be a little bit subtle. So we want to count. Let me fix a little bit of data first. So write M1 as summation, let's say A1I di star. M2 is summation A2I di star. And n is equal to summation bi di star. So these are just remembering that b lies in this dual vector space spanned by the di stars. We can do this. These are all integers. A1I is an integer, A2I is an integer, bi is an integer. And we also have a strata. So let D out, let D out, close that out, be the intersection over all I such that BI is non-zero of DI. So that's the stratum more or less determined by N. This is by definition non-empty. Otherwise, this would not be lying in a cone of the dual complex. And pick a general point. Z in Z apt. Okay, so we are interested in maps. We are interested in counting stable maps, which I'm going to write as f from C with 3 marked points. I'll write as x1, x2, x out to x. That's our target space. Our x is our log Fabio, where the genus of C is 0. And now I'm going to give, well, okay, I'm going to give something a little bit vague, and I'll try to sharpen this a bit. F has contact order A1I with the divisor DI at x1. F has contact order A2I with DI at x2. Finally, f of x out is constrained to be equal to z. So the output point x out maps through to z. And f has contact order minus bi with di at x out. Okay, what does this mean? Well, let's start with a big problem. So what is contact order? So let me talk about contact order just if we imagine x is just a smooth variety with a smooth divisor d. So if you have a curve, let's say a curve that doesn't fall into D, or a stable map, so F is a map from C to X, with image being what I've just drawn, it makes sense to ask, well, what's the degree of tangency of this curve with C at a given point? And how do we define that? So if X and C is a marked point, and f of x is in D, let's let t equal 0 be a local equation for D at f of x. So t is some function on x that cuts out D, that defines t equals 0, defines D locally. So I can then look at the function t composed with f. This vanishes at x to some order. Called the contact order of f at x with the divisor D. So for example, in this picture, I intentionally drew this branch to be transversal. So at this point, you would expect the contact order to be 1. So in other words, the local equation t equals 0 pulls back to an equation for the point, an equation which is a function that has a simple 0 at that point. Whereas this branch of the curve you see is tangent to D, so maybe the local defining equation for D pulls back to a function that vanishes to order 2 at this point on the curve. And that's the contact order. Okay, so here, if I go back to this, this description here, that now at least explains these first 2 points. I'm going to insist that this point x1 has contact order given by this coefficient a1i in M1, in M1 there. So you can think of this as dictating some contact orders for a stable map with the various irreducible components of the boundary division. And similarly at x2, we have some contact orders for those points. Both very well. We have this point constraint f of x out has to map to z. But then we have this crazy thing here. Right? Let me really emphasize this is a minus sign here. I'm now suddenly saying we have negative contact order. And that doesn't make any sense because I'm pulling back an equation t equals 0 to the curve, and that's not going to hold. It's only going to have zeros. So to make sense of this, we need to use the punctured, not use the word dot there, we need to use punctured Witten invariants, which were defined by Abramovich, Shen, myself, and Siebert. So the theorem here is that these invariants can be defined and the above product rule turns this ring Ri, or this module, turns the AI module Ri into a commutative associative AI algebra with the unit beta 0. So this is a 2019 paper of myself and Siebert. So once you have this, given this, we can then define the mirror XD as, or the mirror family, I should say, as spec XI, spec AI. So this is an infinitesimal version of the Kähler modular space. Or we take the limit over all I, and get a formal mirror, if you know about formal schemes. Otherwise, you probably won't be that happy. A formal mirror, let's call it X, over the formal spectrum of completion with the limit over all these AIs. Okay, so this is a rather technical point if you're not an algebraic geometer, but this is the best we can do in general to construct a mirror family to the log-Rabia. It will be a formal object. Okay. So if you haven't really been, if you got overloaded in the details, I'm sort of sensitive to the fact that some of these details can look quite complicated until you start to work with them. you should really have this being the takeaway for today's lecture, is that there is a way. We just start with this this AI module, and we put on a product structure using these funny kind of growth invariants, which involve contact orders with divisors, maybe negative contact orders. I still owe you some deep understanding of what those growth invariants are, and that's going to be the main thrust of the next lecture. And if I have enough time, it will also allow us to understand what the original scattering diagram, what the correct scattering diagram to use is. Now, I could have started this whole story by just saying, let's start with this pair XD, we take this B, we take this, once we have B, we have this ring or this module, and then I could tell you about this product world without having gone through the last 3 hours or so of lectures. But my goal was really to explain how we got to this point. Why is it reasonable for this kind of gadget to actually have anything to do with the mirror? It's because we had this sequence of ideas about how instant-on corrections are supposed to allow us to understand what the mirror is. And that was what I hope I got across. So next time I will get into the nitty-gritty of how we start to define these kinds of growth invariants. And I hope I'll have time to finish the story.